Go.
Okay, yeah, thanks. Yeah, I'm happy to be able to present this in person. As you said, this is about 2 years old, so we'll have some newer results at the end. And this is work together with my advisor, Heather Miller, and another PhD student, Christopher Mickeljohn. So to start off, our setting is that you imagine you're making some sort of web service where you have shared state and multiple users can interact with that shared state. So that's pretty much any website nowadays, but some examples I have in mind are things like Google Docs, Slack, Facebook groups, that sort of program. So the traditional way you implement this is you have a server. When some user wants to update the shared state, they'll send a message to the server. Server will do some processing, send a message back, and then the client updates its own view of the display, showing the new changes. So of course, in real life, it's usually not one server. It's actually this distributed system made of a bunch of servers in the cloud, and they're all communicating using message passing. So a lot of work has gone into making these cloud systems easier to program, but it's still pretty difficult. There's a lot of different components. You need a lot of specialized knowledge to write the server code, and it's really easy to introduce bugs. So CRDTs are an alternate way to try to manage shared state in these sorts of programs. It stands for conflict-free replicated data types. And basically, these are data structure where there's constructions that look like ordinary data structures, except they're shared across multiple devices, and under the hood, they sync up with different copies intelligently so that all the users stay in sync. So to see what this looks like from the programmer's perspective, here's a code snippet using the Legion CRDT library. So this is client-side code that you'd run in the browser. The first two lines here set up the group and basically connect the users to each other. And then on the third line, we want to have a set to represent a shopping list. Instead of creating an ordinary set, we create a Legion CRDT set with this line here. And then when you want to manipulate it, like if one user adds milk to the shopping list, you just say, shopping.add milk. What this will do under the hood is on the original user's device, the one who's performing this operation, they'll update their local state immediately. So their browser will immediately show milk in the shopping list. And then lazily, sort of in the background, it'll also broadcast this change to other users. When other users get this broadcast message, they'll update their own state to show milk in the shopping list. Yes, that's the basic idea of CRDTs. And what I like about them, PowerPoint's mess up the formatting a bit, but basically they're a programming language's way of solving a systems problem. So we have the systems problem that we have a bunch of devices, and we want to share state between them. And CRDTs say, okay, we can take this hard problem, put it inside an abstraction that has a nice data structure like API. In particular, these CRDTs are designed in a principled and mathematical way with proofs of correctness and consistency. So at least in theory, it should make it harder to introduce bugs. So some pros of using CRDTs, they have this simple client-side programming model. In the limit, it should be almost as easy as writing a single user application. You just swap out your data structures for CRDTs. In practice, it's a bit harder, but that's like what we're aiming for. You can do local first software in the sense of like InconSwitch's local first SA, where you have offline support, data exists on end user devices. Let's see, you can tolerate high latencies. You can even use CRDTs to do end-to-end encrypted web apps. Like I worked over the summer interning at a company that makes a Notion-like app, like a collaborative notes editor that's end-to-end encrypted. Under the hood, they're using CRDTs to manage the state, and then they just encrypt the lazy broadcast messages that are being sent around. And disadvantages of CRDTs, so they're really designed for data shared in small groups, basically because every device is processing every update from every other device. So here we're really thinking, like Google Docs or Slack, not Twitter. They're not for data that needs locking. In technical terms, CRDTs are eventually consistent, or really strong eventually consistent, whereas for things like monetary transactions, you really want strong consistency. And apologies for the overlap. So the thing that we're going to talk about in this talk is the challenge that if you want to use CRDTs, you need to design some sort of conflict resolution algorithm for each data type you want to use. Basically, the problem is because we let users update their own states immediately and propagate updates in the background, you might have two users concurrently making changes to the same state, which sort of conflict with each other. And if that happens, we need to resolve the conflict, make it conflict-free, and that requires making some choices, designing some algorithms, proving things that are correct. And this is a difficult and ad hoc process. So in practice, what it means is you're restricted to whatever CRDTs people happen to have designed and implemented over the past 15 years. This is the problem we try to address in our work. In particular, we present a compositional design technique for CRDTs that we call the semidirect product. So what it lets you do is take some existing simple CRDTs and compose them into a bigger, more complicated piece, hopefully in a way that's hopefully easier than trying to design a CRDT from scratch. So in detail, we take two CRDTs, C1 and C2, we assume operate on the same state type, like maybe they're both numbers or both sets. We, for technical reasons, require this function called an action, and then we output a new CRDT, which has the same state type as your inputs, but now it supports both of their operations. So for example, if the CRDT on the left supports addition operations, the one on the right supports multiplication operations, now you get a CRDT that lets you both add and multiply, and if add and multiply operations happen concurrently, it'll try to resolve this conflict in an intelligent way. So one thing you can do with this is composition, which is composing up bigger CRDTs, or in practice more often it's like take an existing CRDT, add some cool new operation that the users can perform, like a new mutating method. So we have some examples in the paper. We take a counter that supports addition operations, we add the ability to do multiplication operations. We take a list that supports insert and deletions, like for text editing. We add this global reverse operation that reverses the whole list. We also have, well, this isn't in the paper, but a later example I'll describe in this talk is you take a particular kind of set, which has operations to add and delete elements, and we add a for each operation that says for each element in the set, do something. You can also use the semidirect product for decomposition, basically explaining existing CRDT designs from the literature by saying, oh, actually, this CRDT is a semidirect product of these two simpler CRDTs. And that should, we hope, sort of like explains the semantics that are coming out of these designs in a uniform way. So before getting into an example of the semidirect product, just want to give some more detail about CRDTs and this idea of conflict resolution, conflict freeness. So recall our system model. When one user makes an update, they update their local state immediately and broadcast an operation to other users in the background. So the problem with this, as I mentioned before, is you might have users make conflicting concurrent updates, like maybe Alice and Bob share a numeric value. Alice sets the value to 3, concurrently Bob sets the value to 5. They sync up and exchange messages, and now they see that there's a conflict. So we have to decide what to do about this. And there's two general conflict resolution techniques that you can see in the CRDT literature. So one of them is to try to make operations inherently commute. So maybe Alice and Bob, when they said set the value to 3, they were actually trying to count something, like I don't know how many apples are on their shopping list. So Alice really wants to add 3 to the value. Bob wants to add 5. These operations naturally commute. No matter which order you apply them, you get 5, or you get 8 rather. So users can just apply the operations literally in the order that they receive them, and even though they receive them in different orders, they get the same result. Another technique is trying to reason about causality. So I'll describe the causal order a bit more on the next slide. But the idea here, like a simple example, is let's say Alice adds milk to the shopping list. Bob sees this, he goes to the store, he buys some milk. So now he removes milk from the shopping list causally later. So now other users will make sure that they also apply these operations in the same order. Add milk first, then remove milk, so they end up having nothing in the shopping list, and everyone gets the same answer. So the causal order is just like a brief technical digression because it's important for our construction. So this is a partial order on the operations performed by users, defined as follows. So here, Alice, Bob, and Charlie are 3 different users. Time goes to the right, diagonal arrows are message sending. So if we have 2 operations by the same user, like here Alice does add milk and later add spread, then we say the first operation is less than the second. Second rule, if Bob receives a message from Alice and then sends his own message, then we again get this less than relation. Add milk is less than remove milk. And the third rule is transitively. We have add milk is less than remove milk. Remove milk is less than add eggs by the first rule again, same messages or 2 messages from the same user. And so add milk is also less than add eggs. So note that with these rules, it's possible to have concurrent messages, that is, messages that are, or operations that are incomparable under the causal order. They're neither less than nor greater than each other. Like here we have 2 concurrent add milk operations. So the use of the causal order in CRDTs is that everyone in the system agrees on the causal order of messages, even if they don't agree on an absolute order of messages, which means that when you compute the CRDT state, you're allowed to query the causal order. For example, the classic add when set CRDT says the state of the set is the set of elements X, such that there was an add X operation in the history, which is not causally less than any remove X operation. So in this example, we can see that milk is in the list because both Alice and Charlie have added it to the list, but only Alice's addition was actually removed. Charlie's addition operation was concurrent, it was removed, so it's unaffected by it. Okay, so that's the causal order. As I mentioned, you can reason about causality to try to design your CRDT, try to avoid conflicts. And our semidirect product basically provides a uniform and reusable way of reasoning about the causal order so that you don't have to. So as you can see, the causal order is, sometimes it's intuitive, sometimes it's a bit complicated. You don't have to reason about it from scratch. It can also be difficult to implement these rules directly. Like, okay, I have a history of operations in a causal order. I need to actually compute the result, ideally without looping over the whole history of operations every time. So our semidirect product construction gives you a way of doing this. And then this leads to a new CRDT design workflow. Instead of starting from scratch, you take your data type, you take its operations, basically partition them into subsets that naturally commute, because those are easy, they're already CRDTs, and then stitch them together with semidirect products. The semidirect product will deal with this sort of causal reasoning between operations that don't naturally commute. Okay, so now, in our experience, this works for many existing CRDT types plus some novel ones. So now let's see it in action. So I'm just going to give an example of the semidirect product. You can see like the full details in the paper of what's going on, but I think this is a nice illustrative one. So we want to make a very powerful number. It's a number that you can add and multiply. In particular, we're going to take the semidirect product of one commutative data type, an integer register that supports addition, another integer register that supports multiplication, and then semidirect product them together. So to illustrate what you might do with this register, you say one user, right? Yeah, one user says, okay, starting at state 1, let's multiply by 3, then add 1 to get 4. So the add operations alone are easy, they already commute. Same with multiplication operations, but they conflict with each other. If you have, say, Dave multiplies the state by 3, while concurrently Mary adds 1 to the state, if they just apply these operations literally as they receive them, they're going to get different answers because these operations don't commute. So let's choose that in a situation like this, effectively additions come before multiplications. So here Mary is on the right, she has applied this add operation before the concurrent multiplication operation, and Dave is wrong. So Dave needs to patch up his result, and our observation is that all he has to do is transform his add operation by the old multiplication operation by changing add 1 into add 3 times 1. So that looks like this. You can check that we get a result of 6 in either case, even though it's a different trace. And the rule for this is basically just a distributive law. Mary has performed 3 times 1 plus 1. Dave has performed 3 times 1 plus 3 times 1 again. And these are identical just by arithmetic. So in more complicated situations, you can have something like this where we have both multiplication and operations concurrent to each other in multiple ways. And the rule we make is just that when you receive an add operation, first transform it by all of the concurrent multiplication operations you've already seen. So this example, if we walk through, when Dave receives multiply by 3, he does it normally. If he receives add 4, he transforms it by his concurrent mult2 operation to get add 8 for a final result of 17. Meanwhile, Mary receives multiply by 2, applies it normally, then receives add 1, transforms it by her mult3 operation, and you can check, even though it's maybe not obvious at first glance, indeed we get the same answer at the end, which is 17. And this is a general rule. We have a proof of this in the paper. It basically follows from distributivity. More generally, we said, okay, add m operation, when you receive it, becomes add n1 times etc. times n, or multiply n1 through nk, are all of the operations you previously received that were concurrent to this new operation. So it's a bit of a funky rule, but it works out. As I said, we have a proof. And more generally, you can do this with any 2 pair of CRDTs together with an appropriate transformation function, or we call it an action, that has to satisfy some algebraic constraints analogous to the distributive law. And I'll give some examples later, but you can use this for things like inserting rich text characters versus formatting rich text characters, translating a shape in a PowerPoint slide versus rotating a group of shapes. They have the same sort of distributive property so that we can make the conflict freeness work out. Okay, so right on time, that was the original 15-minute ICFP talk. Now, since we have extra time, and it's been 2 years more, I'll have some new results extending this paper that I want to talk about. So the first thing, or one of the first things people ask me after the original presentation is, what is the meaning of the semidirect product? Like, what is the semantics? If I'm a user using an application and it's using a semidirect product under the hood to resolve conflicts, what's going to look like to be? Will it make any sense? So in particular, James Riley from DePaul asked, how does the semidirect product relate to the behavior of some sequential data type spec? I guess the idea is that the ground truth for any data structure is just what it does in the ordinary single user case. You're just applying operations as they come in. And typically you want the CRDT behavior to be related to the original data type. Even if you have to make some changes for the concurrent setting, it should really be simple changes like reordering operations, something that makes sense to users. So my answer at the time was like, I don't know, I hadn't thought about this question. And it wasn't really obvious that semidirect product is related to any sequential data type specification. In particular, the hard part is that you might attempt to relate the semidirect product by saying, okay, if we have a history of operations, take this causally ordered history, break ties in the causal order using this adds before concurrent mulch rule, and then just like take some linearization of this, evaluate it in order to get the answer. The problem is you can't always do this linearization. Sometimes you get cycles in the dependency graph. In that case, you have to decide to do something else. So semidirect product says use the actions to transform the operations as they come in, and you'll get a consistent answer, but maybe a weird one. Other papers say other things. These are some papers that have different answers. And it's not really obvious to me that any of these papers, including the semidirect product, are really doing the right thing or like an intuitive thing. So more recently, I think I have an answer to this question, which is that, okay, yes, the semidirect product isn't really doing anything intuitive, but our best examples are all basically specializations or maybe generalizations of one particular construction called the unique set with for each hops, which I now want to explain. So to start off, this unique set, this is sort of a folklore CRDT. I don't know a proper name for it, so I just call it a unique set. If you're familiar with list CRDTs, it's basically a list CRDT where you ignore the order. But yeah, as a sequential data type, it's like a set of elements with reference identity. So each element is unique, even if they happen to have the same value. You have operations to add and delete elements. In the concurrent setting, you can do the same thing. People just add and delete elements, and they sort of operate independently. You can also make a unique set of CRDTs where the values are themselves CRDTs. This means you have operations to add a new CRDT, which is like a distributed new operation. You can delete an existing one, which is like a distributed free, or you can perform an internal operation on some value CRDT. For example, so okay, this is actually a list CRDT. Again, this goes to a unique set, but you can make a rich text document out of a list of rich character CRDTs. So each of these characters is its own CRDT. You can create a new character, you can delete one. You can also operate on them by saying, make this character bold, make this character have a different font size. And those would be internally managed by a per character CRDT, and put the whole thing together into this unique set of CRDTs. So now sequentially, we have an extra operation we can do besides add, delete, and internal value ops. We can also say something like, for each operation, do something. For example, in rich text, you can say for each character in the range, make it bold, which involves applying a bold operation to the per character CRDT. In a collaborative setting, we have this extra option where we can say, okay, I actually wanted to make every character in this range bold, including ones that were added to the range concurrently. So here maybe we start with the sentence, the cat jumped on table. On the top, Alice wants it to make it bold. On the bottom, Bob is fixing the typo by adding the word the. So they're both doing these operations concurrently, maybe with a second of network latency. Later they sync up. We'd really like the result to be that the whole thing is bold, including the new word the, otherwise it would stand out kind of awkwardly. So that's what you can do with one of these for each operations. You say for each character in the range, including these new ones that were added concurrently, make it bold. For lack of a better name, I call these a causal plus concurrent for each operation, because it's a for each operation where you apply it both to causally prior values and to concurrently added values. You can exhibit it as an example of a semidirect product. Unlike general semidirect products, it actually has a nice user-friendly interpretation. It's basically just this picture on the previous slide. You do the obvious thing, say, do it to concurrent operations as well. And sort of by empirical observation, or really more just assertion, is that many of the useful semidirect product examples we have are actually just instances of this for each thing. They correspond to some set of CRDTs where the operation added by a semidirect product is just saying, for each element, including concurrent ones, do something interesting. And then if you actually use the semidirect product construction directly, you can get some like optimized state stuff or state size stuff, but I don't know if the optimization is really worth the conceptual cost of having to do something weirder. Okay, so that's it for theory stuff. If you've zoned out, now is a good time to zone back in because I'm just going to talk about some code. Okay, so we implemented the library, we implemented the semidirect product rather in a new library. We call it Collabs. The docs website is here because we even have a docs website. It's a TypeScript CRDT library that's designed to make it possible to build collaborative apps on top of CRDTs, similar to AutoMerge or WatchJS if you've heard of those. But unlike existing libraries, it supports both custom CRDTs and composition techniques. And the reason we did this is because we need it for the semidirect product. Like if you want to make your own cool CRDT as a semidirect product, you need to be able to make the pieces as custom CRDTs, like maybe commuted data types, and then you need to be able to compose them together. So we have a semidirect product for that. We also have more straightforward composition techniques like, make an object out whose instance fields are CRDTs and then do some OOP encapsulation. And yeah, if you can read it, so it's kind of hidden here, but there's an archive preprint I put up yesterday that describes the sort of like the theory behind the library in more detail, and also some of our examples and stuff. This is not just me, by the way. I guess I started about 2 years ago, but also had help from a lot of students at CMU and otherwise. And now some demos. So that we have 2 demos using the library that make use of semidirect products to do something cool. So the first one is a rich text editor. You can see here a GIF of using it in action. This is under the hood. It's doing like end-to-end encrypted, decentralized collaboration using the matrix.org chat protocol. And we use a semidirect product for exactly the thing I've been talking about. When you bold a bunch of characters in a range, we want to also bold concurrently inserted characters. So technically, this is done by, we have this rule that when you insert a new character, it inherits formatting from its left neighbor. And then if you have a formatting operation and an insert operation, you do the format first, then the insert to make sure that this formatting can be inherited if needed. Yeah, this I did not figure out. Jordy figured out how to do the semidirect product and integrate with Quill and all that, which is really the hard part. Another demo, we have this intuitive but sort of hard to describe behavior that you might want in, say, collaborative PowerPoint. Let's say you start with 2 shapes. One user moves the shapes a bit farther apart. The other user concurrently rotates the group of shapes. What we'd really like in the end is that the shapes should be translated first and then rotated, as opposed to, say, rotating both shapes in place and then moving them farther apart, which would look kind of weird. This is, again, a semidirect product where we basically impose the rule that if you have concurrent operations, then this individual shape translation should happen before rotating the whole group. Actually, technically, we need like a multi-level semidirect product because there's translations, rotations, and reflections. That gets a lot trickier, but we, an undergraduate student who worked with us really saw this through. Okay, so to recap, CRDTs are a nice programming language's way of solving a systems problem, that is how to build systems that act on shared state. More info about CRDTs in general at this nice website, crdt.tech. Our semidirect product is a compositional design technique for CRDTs, which in principle lets you do this new CRDT design workflow of design simple commutative data types for subsets of your operations, and then glue them together with semidirect products, which will reason about causality. We can implement this in our TypeScript library, Collabs, and on further reflection, maybe instead of the semidirect product, we really just need this unique set with its concurrent plus causal for each operations. Yeah, thanks for watching. I welcome any questions, and if you want more info, I have a bunch of links on my personal site. That's it.
Well, thank you. Right, do we have local questions? Do we have a microphone for?
No, we don't have a microphone.
Okay, so
Yeah,
how should we handle that? Or maybe you just repeat
yeah,
it.
I can try.
Yeah.
Sure.
I think that's the best.
Yeah, let's do that.
Yeah, so my question is simply, would I, as a user of the semi-direct product technique, would I be able to define this arbitration order? So could I say I want my ads to be applied after multiplication, for example?
Yes, so the question is, as a user of the semidirect product, do I get to choose the arbitration order, like whether ads go before mults or vice versa? So the answer is not quite. You get to choose the action, and the structure of the action will agree with one or another arbitration order, but only certain actions actually work. Like I think you're saying molds before ads. I don't know of any action that will actually work with that. Whereas ads before molds works with the distributive law nicely.
Maybe a follow-up question. So what do these actions actually do?
Yeah, the follow-up was what do the actions do? Yeah, so that was, it's probably too far back to go. But remember we had this rule, when I receive an add operation, I transform it by concurrent multiplication operations that already happen. So that's the action. The action is a function that takes as input a multiplication operation and an add operation, outputs a new add operation. That's like the transform version. Yeah, it's a restricted and simplified case of operational transformation, if you're familiar with that.
Go ahead.
Okay, so I might have missed it, but you mentioned in the introduction that this semidirect project point of view on CRDTs could also be used to understand existing constructs.
Mhm.
And do you have any example for that?
Yeah, the question was about examples of using the semidirect product to understand existing CRDTs. Yeah, so in the paper we have the add when set and remove when set, which are two classic CRDTs. Basically decompose them into their add and remove parts, and then use the semidirect product to arbitrate the conflict between adds and removes. There's another example that involves like resetting behavior. If you're familiar with React and the React map, they have this rule where you have a map from keys to value CRDTs. If you delete a value, then it gets causally reset, like all prior operations are gotten rid of and new ones are kept. So we also explain that as an example of a semidirect product.
Any more? Do we have something online?
Yeah.
Okay. Yeah, so I have one question. So you said essentially that it's some kind of distributivity property that you need.
Mm-hmm.
Is it distributivity, or what exactly is the transformation that you, the law that you require?
Yeah, I think it's basically the same as distributivity, and there's just some caveats, like you only need it for operations that could be issued concurrently, and that are these two different types. So like it's possible to have a rule that says like, okay, the type 1 and type 2 operations don't distribute over each other if they were issued sequentially, like by one user in a row.
Mm-hmm.
Yeah, it's like a slightly weakened form of distributivity just to deal with causality, kind of like how CRDTs in general are like a slightly weakened form of a commutativity or like a Abelian monoid rule, where you also get to have exceptions for sequentially ordered messages.
So is your toolkit, if I can call it that, is it in some sense complete, or are there CRDTs that you would still have to design from scratch now?
There are ones that you still have to design from scratch, and they tend to be
like what?
Let's see. Well, so one example I have in mind is this rather complicated CRDT for dealing with group membership. Basically, like group membership is a tricky problem in a distributed group where users might do nasty things like try to remove each other concurrently. So there's a way to solve this problem, which has to do with like looking at the history of operations and trying to break cycles in an intelligent way. I don't think that can be expressed in terms of semidirect products at all.
Mm-hmm.
There's also lots of implementation strategies that are maybe semantically equivalent to a semidirect product, but under the hood are way different. Like the paratext rich text CRDT is way different from the way I described to do rich text here.
Okay. Question. Thank you again. Very nice.